Welcome back, everybody, to this first plenary of today's last day of the Global Space Exploration Conference, GREX 2021. And this first plenary of today has been organized by the Space Research Institute of the Russian Academy of Sciences, and it is titled Human Roads to Outer Space, Real and Imaginary Dangers. The panel will feature on-site and remote speakers, and it is moderated by Mr. Anatoly Petrukovich, Director of the Space Research Institute of the Russian Academy of Sciences. Anatoly, please, the floor is yours.
Okay, dear colleagues, dear Professor Fechtinger, our session today is devoted to the perspectives of safe human presence in the outer space. In the outer space, it is beyond the near orbit. And currently, outstanding progress of space medicine after 60 years of human flights allowed long-term presence of about 1 year and a half in the microgravity field and space radiation of the low Earth orbit. Outer space flights, first of all, have the risk of the much lesser shielding of the Earth's magnetic field on the space radiation. And the limitations of a human survival in the radiation of the solar system are very challenging. This will be the first topic of our panel. For example, debates are still underway when conditions are more favorable for Martian expeditions during solar min or solar max. Other problems are special gravitational conditions at the Moon. While human adaptation to microgravity is rather well understood, mid-term, several months presence of humans just in a small gravity will definitely require very difficult accommodation scenarios and research. Finally, as one more effect of the outer space, which is often mentioned if we work on the Moon, is lunar dust. It is a very aggressive toxic substance consisting of fine and sharp charged particles, which is known to affect the operations outside the lunar base. This list of main dangers can be even larger. But whatever the dangers are, they should be met by medicine and by some precautions, by some research, and by some methods during the human presence in the outer space and after the space flight. This will be the second half of our panel. Finally, I would like to welcome our participants. Here in the hall, we have on the side, we have Oleg Orlov, Director of Institute of Biomedical Problems of Russian Academy of Sciences. That's our main organization responsible for medical support of the human spaceflight, and he is also academician of Russian Academy of Science. And Professor Valery Kolegaev, head of the Laboratory of Space Research at Moscow State University, the leading Russian institution for space radiation studies. On the web, remotely, we have presence of Professor Ioannis Douglas, president of the Hellenic Space Center from Greece. He is also specialist in space radiation. Hans Christian Gunga, deputy director of Institute of Physiology, Center of Space Medicine and Extreme Environments in Berlin, Germany. And Professor Bingxian Liu, associate professor of National Space Science Center, Chinese Academy of Sciences. He is also representative of the radiation community. Unfortunately, Lev Zeleny, president of Space Research Institute, Russian Academy of Science, was not able to join us today for technical reasons. So we just start with radiation. And the first panelist to speak is Professor Bingxian Liu. Please.
Hello? Can you show my presentation? Okay, thank you. Good morning, everyone. I'm glad to have this opportunity to talk about human health risks in deep space missions. I will use human Mars exploration as an example, talking about radiation effect. Next, please. The radiations mainly include galactic cosmic rays and solar particle events. The GCRs are mainly protons, alpha ions, and heavy nuclei. The flux is lower during solar max, but higher during solar min. Solar particle events are caused by solar eruptions. The main component is low to medium energy protons, but SPEs are frequent during solar max and rare during solar min. So, with regard to radiation, it is a question when it's better to implement human Mars mission. Next, please. Here, we use a 3-year Mars mission scenario to analyze the radiation effects of GCRs and solar proton events. We assume a 1-year transit time from Earth to the Mars, a 1-year stay on the Mars surface, and a 1-year transit time from Mars back to the Earth. The left figure shows the energy spectra of GCRs during solar min and solar max, based on the CRAM 96 model. The right figure shows the energy spectra of the solar proton events in 2003. This is the solar max of solar cycle 24. Next, please. We use Gen4 to analyze the effective dose equivalents under different shieldings. Left table shows the doses in the interplanetary. As the shielding increases, the SPE dose decreases fast. The remaining dose mainly comes from those with harder energy spectra. For GCRs, the dose also decreases as the shielding increases, but not as significant as SPEs, implying that we may need other shielding methods, such as composite materials or active shielding. The right table gives the doses on the Mars surface. The Mars atmosphere is equivalent to an aluminum shielding of 20 grams per square centimeters. The main dose is still from GCRs, but solar proton events with hard spectrum also contribute. Next, please. According to the results in the above two tables, we can estimate the effective dose equivalence during solar max and solar min. It can be seen that total dose during solar min is higher than solar max, and under the shielding of 10 grams per centimeter square, it may exceed the standard given by NCRP 98. During solar max, in the interplanetary space, both GCRs and solar proton events are important radiation factors. On the Mars surface, the dose of GCRs is much higher than SPEs, but solar proton events with harder energy spectra cannot be ignored. I would like to say that this is a very preliminary estimation, and further detailed analysis will be carried out. Thank you.
Thank you very much, Professor Liu. And this radiation issue is actually very multifaceted. We have several components of the radiation in outer space. The one which was known about 100 years since the first airborne experiment is galactic cosmic ray radiation, which is relatively stable and just a little bit modulated by solar activity. With the start of the space flight, one of the first discoveries were radiation belts, which were one of the largest surprises of the first years with the first launches of the first spacecraft by Soviet and American scientists. And finally, we have solar cosmic rays, which are sporadic, but could be very intense. So the next view on this problem is by Professor Douglas. Please.
Good morning. I would like to thank the organizers for inviting me. I regret that I am not in St. Petersburg today. I would love to be there, but unfortunately it has not been possible for me. So the issue of our session today are the dangers and the hazards and the risks. So a general comment on the risks. The risks are, of course, related to the difference of various conditions according to the location, like, for example, lower gravity or lack of oxygen or low temperatures. So this is just a difference in the conditions. But of course, the risks are also related to various hazards, such as ionizing radiation. And we have to understand both the character and the detailed spatiotemporal properties of the hazards of the environment that we intend to explore or to use in order to effectively mitigate all associated risks. The risks are related both to technical infrastructure and to our own bodies. And both are very important, because if the infrastructure fails, then this will have an impact also on the bodies, on the health of the bodies of the astronauts. By quantifying the hazards and consequently estimating the risks, we can design the appropriate protective shielding. Some hazards have more complicated properties and are more difficult to predict. So the main hazards we are aware of, the main interplanetary hazards for any mission beyond the protection of the terrestrial magnetosphere, we already heard, are galactic cosmic rays and solar energetic particles. I would say that photons, hard photons like X-rays or gamma rays, are at least within the solar system and within, for the foreseeable future, not a significant hazard. And the associated risks, the associated biological risks, I guess that we will hear about them later from other colleagues, but just them are two categories: the acute effects, which are of deterministic nature, and they refer to malfunctions of various organs, and there are specific threshold doses for them, and also late effects, which refer to DNA damage, mutations, and cancer development, and they are stochastic with no specific threshold doses. Next slide, please. This is a well-known property regarding the relative biological effectiveness, and these are graphs comparing the relative biological effectiveness of particles, protons in this case, and photons, X-rays, and they refer to the survival percentage of cells, of living test cells, experimental cells, on bombardment by particles and X-rays. So this just demonstrates that particles are a major concern for any manned mission beyond the Earth orbit. Next slide, please. Mentioned the relation of rays and solar energetic particles. This is a graph showing this anti-correlation over a few solar cycles. On the top panel, we see the sunspot number, and we can see 3 consecutive solar cycles. The second graph shows energetic protons as detected by the IMP spacecraft at L1. And we can see that we have a lot of solar energetic particle events around solar maximum, a well-known fact. And the flux is also really high, especially when compared to the cosmic ray flux, which is the bottom, which is the solid line on the bottom panel, where we see that the cosmic ray flux has maxima around the solar minima. We can clearly see it. And it is also interesting to note the sporadic events on the lower panel, again, on the lowest panel, of very high energy solar protons with energies above 60 MeV, which are again much more abundant around solar maximum. And this poses the well-known issue of choosing the right time for an interplanetary mission, because around solar maximum we have sporadic but intense, very high flux solar proton events, and around solar minimum, when we do not have the solar energetic particles, we have a higher flux of cosmic rays. Next slide, please. So this is just a thought on how how we could contribute to the safety of a manned mission through an example of robotic missions. This simply shows that a solar energetic particle event that has been detected at Earth, at the Earth orbit by geostationary spacecraft, propagates, of course. I mean, solar energetic particles do not stop at Earth. They continue to propagate in interplanetary space. In this particular, we see that a problem created by an SEP event was registered at GOES 8 and GOES 9, two geostationary spacecraft. And 2 hours later, it was registered at Cassini by the Cassini spacecraft, which was, of course, beyond the Earth orbit. So in principle, robotic spacecraft could be used for alerting manned missions which are beyond Earth orbit in order for them to take precaution measurements to protect the crew. So thank you very much. I think that was my last slide.
Thank you very much, Professor Douglas. So the final speaker on radiation issues is Professor Kalegaev. Please.
Good morning. Could you please my presentation? Okay. After the talk of Yanis Douglas, I would like to describe the condition in the geospace inside the Earth's magnetosphere. Next slide, please. And could you please show presentation on my screen? Oh, okay. Okay. Just after the first space experiments, scientists understood that space is filled by energetic charged particles, and we should take into account this fact when we plan the space missions. Please, next slide. If we look inside the magnetosphere in the near-Earth space, we can see here 3 different populations of energetic particles: galactic cosmic rays, solar energetic particles, and also radiation belts. Energetic particles coming from the Earth and from the galactic, you can see here declined by Earth's magnetic field. This is our shield, and we are lucky that we have such a shield in our magnetosphere around the Earth. But actually some orbits of spacecrafts, geostationary orbit and LEO orbit, are partially influenced by these particles because energetic particles penetrate to high latitudes. and they modulated by solar activity as well, and in different times we can see the different regions of penetration of particles. Also, this region depends on energy. More energetic particles can come to the lower latitudes. For example, 10 GeV particles can go to equator, but fortunately this flux is very low and don't include it in the dose rate for the spacecraft or electronics. And existence of the magnetic field also the reason for existence of radiation belts, because we have some places in the magnetosphere when we can measure energetic particles anytime. Next slide, please. Earth radiation belt consists from energetic electrons and protons, and we can separate two regions in geospace filled by particles of different nature. Inner zone, inner radiation belt consists mostly from protons, energetic protons, and electrons still several MeV. This region is responsible for multiple single event effects, influence on electronics. Radiation belts are not symmetrical due to features of geomagnetic field, and we have one region, South Atlantic anomaly, which intersected by low Earth orbits anytime, and also International Space Station are often coming through this region, and this is the reason for radiation dose collected by cosmonauts on International Space Station, in addition to galactical cosmic rays. Outer zone is mostly consists of electrons, and it is very dynamical region, dependent on solar activity, on condition in interplanetary space. During magnetic storms, during fast solar wind fluxes, streams, we see enhancement of fluxes that are responsible for inner charging of spacecraft. Next slide, please. As about the galactical cosmic rays, we know from previous reports that this is one of the important factor for a long time missions, but also it influenced the biological tissues, starting from the Earth's surface. We know that the dose for the people on the surface is about 1 millisievert per year. Actually, during the flights on the through the polar region, we can get 10 millisieverts per year, and for the astronauts on the International Space Station, the dose rate is about 200 millisievert per year. But when we come to the long flights, for example, for Mars, we can get a lot of radiation dose, about 1,000 millisievert for the flight to Mars. But we don't take into account solar energetic particles. For example, for the event on 1972, during one day, we have about 4 sievert during this event. This is a very high dose rate. Next slide, please. Actually, inside the magnetosphere, we can detect the start of the event by the measurements on the geosynchronous orbit. You can see here the white picture. below, above is Röntgen. This is X-ray detection, and below is particle fluxes at the geostationary orbit. Just during 72 solar flare, the astronaut outside the spacecraft can got 4 sieverts. This is actually a very high dose that can lead to the mortgage of the astronaut. Next slide, please. Thank you very much.
Thank you, Professor Kaligaev. So here we have seen that the radiation effects are very diverse. Radiation, of course, is in colloquial way, from a colloquial point of view of the general public, is the most dangerous aspect of space, besides vacuum, of course. But effects of the space physics are actually much broader. Unfortunately, we are missing today Professor Lev Zeleny. His plan was to speak about 2 main issues. I will just briefly name them. The first one is the issue of lunar dust. If cosmonauts or astronauts or taikonauts or somebody else, some other representatives of some other countries are working on the moon surface in the spacesuits, they should expect to bring some dust back on the spacesuits and on the equipment, back to the pressurized volume. And this results that this substance, which is basically was lying billions of years at just at the surface of the pressureless body, appears inside this volume, which is considered to be a safe, 100% safe zone. And still, we don't understand finally how dangerous it could be in the long run. There was some experience with the astronauts on the moon, but their exposure to the dust was very small, several days. And still they noticed and put it in their reports that it is potentially a very dangerous thing. So this, of course, remains an issue of the future debate and future studies with the automatic spacecraft on the moon surface. We need to understand how toxic is the dust, how it could be mechanically abrasive, and other issues. But finally, whatever is happening with the physical medium in which the person is placed in space flight, the ultimate answer to the human survivability is received through medicine. How we measure the adverse effects of the space on the humans, how we mitigate them, and how we compensate them after the space flight on the ground. So I am giving the floor now to our 2 representatives of medical community. First, please, Professor Oleg Orlov.
Thank you. We have a very interesting discussion concerning so-called new factors of influence of space on human body, which we'll meet when we go in outer space. Radiation, dust, if we're speaking about moon missions, and one more factor, hypermagnetic field or absolute absence of magnetic field in outer space, which is one of the high problem risk for future interplanetary main missions. And we had discussed a bit about this problem too. But if we move forward and try to classify the risk of such interplanetary missions, we should say it about the problem of autonomous of such flight. Interplanetary missions have the problem of growing autonomous of management support of such flight. That means that we should change absolutely even the principles of medical support of such missions, and they cannot be organized on the basis of our experience on the lower orbit. Then we should modify the prophylaxis system which is now used make it more individual, maybe used artificial gravity approach, and made it more individual managing. So, and then the problem of modifying selection of crew members, which should be based on more personalized approach. If we move forward, we should speak about autonomous of life in outer space. Autonomous of life in outer space, its first problem, adaptation to space. How human, we don't know how human body, the level of adaptation, how adaptation can be developed if we stay in space conditions for a long period of time, because we should use prophylaxis all the time, and we don't know the possibility of physiological adaptation to the outer space, but this question is still open. Then the life support systems, or another approach to resources sensibility using such technique like hibernation, which is under the discussion for now very, very popular team. And then the problem of extension of the human race, which is discussed now, and we are only at the beginning to understand how we can move on with this question. So, but I would like to say that we shall move on step by step, coping with risks, and then real dangers become more and more imaginary. I think so. Thanks.
Thank you very much, Professor Orlov. And our final speaker is Professor Gunga, and his talk will be on a completely different theme, but also very interesting subject, which shows the diversity of the human life, aspects of the preserving human life, safe human life in space. Hans Christian, please.
Yes, thank you very much. I would like to thank the organizers and the chairman to get the opportunity. May I have the first slide to come into my presentation? Yeah, one of the well-known features which are happening during a space flight is the fluid shift from the lower part of the body to the upper part of the body. And it has become more and more clear that during long-term space flights, this might be an issue which was not foreseen some years before. Next slide, please. I would like to address here a problem that might occur from two different sides. And one side is the thermal regulation, and on the other side is that described fluid shift which happens in space. These seems to be far distractive topics, but I think they belong together. What you see here is a situation of the thermal exchange from the human body on Earth with an environment and then in space. And what you see is that we have a different heat transfer on Earth, and in space we have the problem that you can't get rid of your own heat, because there are several layers of different temperature fields around you, and you have no, as we call it, physical convection. On Earth, it's about 600 liters per minute which goes along your body, but in space this doesn't happen. And from that, we expected that the temperature is increasing, especially during exercise. Next slide, please. We developed a special sensor which could be non-invasive, placed at the head. Next slide. This was only to address the sensor. And it is measuring actually not the temperature, but the heat flux measured at the head, at the front of the head. And it's, so to say, the temperature of the brain. And next slide, please. And we had an exercise testing on the International Space Station with European and American and Canadian astronauts. And we looked how the temperature inside the body is changing in comparison to the same exercise conducted here on Earth. Next slide, please. Oh yeah, it's moving, so it's even better than I thought, but we can skip it to save time. So what you see here, we are looking only on the, there you see data from the core body temperature, CBT, so the temperature in the brain, so to say, at rest and at exercise in the upper panel. Oh no, go back, please, go back. And what you see here is that the core body temperature is increasing already during rest, during spaceflight. We measured the first data point 15 days in space and the latest one 165 days in 12 astronauts. And what you see is during rest already, the temperature is higher in the astronauts than pre and post flight. On the right upper panel, during exercise, you see now that during a very short exercise, the temperature is sometimes increasing nearly to about 40 degrees. And that is definitely, for a long-term exercise, that is too high and could be at least in dangerous, come into dangerous levels. And we see it takes about 30 days after spaceflight that the temperatures come back to the normal value. Next slide, please. We therefore looked at whether a certain marker of a temperature increase is increased in these astronauts. And what you see here is a relationship between the core body temperature and so-called interleukin, a special transmitter, which is increasing the core temperature, something like fever. And what we expected to see, and what happened is that we see there's a strong correlation with the increase in the core temperature and these markers of getting a higher temperature inside the body, like fever. So there is some kind of activation which looks like an infection happening during long-term spaceflight. Next slide, please. And here we go directly now into the brain. What you see here is the blood vessels inside the brain and its connections to the next neurons and the nervous.
Maybe it will reload. We have some time, so maybe it will reload in a moment. Yeah.
Back in the
This is the final speaker. We need to switch to questions. I think we will wait a couple of minutes.
Hello?
Okay. Yes, we are here. You can hear you. Continue, please.
Okay. Can I have the slide, please, the last slide?
Yes, please.
Okay. So this is inside the brain. Thank you. And now we look at the problem. Next slide, please. When we have hyperthermia, so if you have an increased temperature, then have the release of special neurochemicals which increase, as it's shown here, brain edema. And this brain edema causes cell injury.
We can see you. Just continue. Slides are on.
Yeah. Okay, the slides are on. So to make it short, this kind of hypothermia, so increased temperature, causes probably cell death injury. And next slide, please. Next slide, please. It is well known now for the last 3 to 4 years that we have an increase in the brain tissue volume due to a fluid accumulation. And I think this is related to the, on the one hand, on the fluid shift, and on the other hand, on the hypothermia which the astronauts exposed during long-term spaceflight. Next slide, please. So I think that the future research should go to combine research due to the hypothermia of astronauts and on the other side, on the brain volume increase in fluid in the brain, known as the spaceflight-associated neuromuscular syndrome, which I think is really, for long-term space flights, for the moment, a very, very severe problem, because the astronauts will need their eyes to work and live on the International Space Station. So thank you very much. I will close here so that we get time for discussion.
Thank you very much, Hans Christian. We have now about 13 minutes for questions. So the last talk just showed us that there is no minor details in the human life in space. Even very simple things which we take for granted at Earth and just don't notice them, can result in some adverse consequences in space. And at least some measures should be undertaken to downplay the importance, to decrease the importance, the adverse effects of these physiological or even physical effects. So we are now switching to questions. We have 3 questions. So the first questions, I will start with the last question, which is appearing here. So, should the first human mission to Mars be with a national or international crew from psychological point of view? So I would like to ask our medical people to answer. Please, Professor Orlov.
Normally, I think that first and next missions to Mars should be based on international level. And I think that future interplanetary missions as a whole will be international level based and have an international crew. That's why we work very hardly with this problem. Psychological interoperability of crew members of such long duration missions. But the last part of the answer is depend on political and economic level, how the first main mission to the Mars will be organized.
Okay, Professor Gungat, do you want to add something?
I actually would fully support the comment from Dr. Orlov, because I think this is really a chance for the international community as well to show how great we can work together and how the different knowledge and experience can be used to really successfully perform such an interplanetary mission. Because I think for the moment the different countries have different experiences, like Russia has during these extensive long-term missions, they have a very, very deep understanding of humans isolated and confined. And some other countries have technical reason or medical approaches. So I think it's a great chance to do this international, and by no means should be dedicated to a national mission at all.
Okay, thank you very much. Now a question for our radiation team. Do any novel concepts exist with respect to shielding? Please, I start with Professor Kalegaev in the room, and then I'll give the floor to the internet.
Actually, now we understood that people in space are under a risk of radiation, and we should create some new ideas about the shielding of people. First of all, we can consider the new materials. New materials can prevent penetration of the particles inside the satellite or inside the shield. Actually, if we look about the more wide shielding, this is not a good idea, because when the shielding is high, we can secondary particles and influence of these particles often more dangerous for the astronauts than for the thin shielding. So new materials, some nanomaterials, can help us to provide more good shielding. Another ideas are technological. We have some ideas about the magnetic shielding, so we should create some magnetic field like magnetosphere around the Earth, more low, of course, that prevent the penetration of particles. But this is very such technological object is very heavy, and now we cannot propose good technological technology to create such shielding. Another idea maybe electrostatic shielding, when we provide electrostatic charge on the surface of satellite that also decline the particles. But this is also a very difficult problem, and now we don't have some approaches to resolving it. I think that we should hope on the future technologies that can help us.
Thank you. Please, somebody else, Professor Douglas, do you want to say a couple of words?
I think that Professor Kalegaev was exhaustive.
Okay.
I have nothing to add. Thank you.
Okay, Professor Luo. No, just microphone, please.
Okay, sorry. Okay. Yeah. I think I heard someone propose magnetic shielding, such just like our magnetosphere of the Earth to reduce the dose of cosmic rays. This is one of the proposed novel shielding. I have no other comments. Yeah, thank you.
As myself a radiation person, I would just add that we are again living in the environment which we underestimate. We are shielded from space radiation by the atmosphere, which is 100 kilometers high, and by Earth magnetic field, which is several tens of thousands kilometers high. And but when we go to outer space, we need to protect by ourselves by the objects which are doable, which are meters at most. If it is magnetosphere, it is kilometers. Mini magnetosphere, it is kilometers. So we by far cannot produce the shielding that is provided by natural means at the Earth. So we have just 6 minutes, and I will I'm asking everybody a question, and I will ask you to answer just how much. Very brief. So the question is, how long will be people able to stay in space, ultimately, in the distant future? Your scientific wishful thinking. So please, Professor Orlov, short answer.
For ages. But the question is the question of price, possibility of human body to adaptate to weightlessness condition, and the prophylaxis system.
Okay, Professor Kalegaev.
I think it depends on the conditions. Too many factors influence on the staying in space. Actually, if the people should be healthier, I think it's no longer than 1 year.
Thank you, Professor Gunga.
Well, I think they could stay longer. We have certain precautions, like we have certain environments created or caves where they can live. I think they can stay even longer. And I think that will be necessary. If we really want to explore Mars, then we have to really think of several years later on to stay there. And I think that will be possible. I'm quite optimistic in that way, that we are able to solve those issues in the near future.
Thank you. Professor Douglas.
Thank you. Well, if we are talking about Mars, if we are talking about Mars and Mars colony, I think that in case we would be able in the future to implement an artificial magnetosphere, which was already mentioned as an innovative shielding method by Professor Kalegaev, then my guess would be that people could stay there for longer times, for many years, and with the gradual adaptation of the body to the conditions on Mars, I guess that in the far future, we could have generations even living on Mars.
And finally, Professor Liu, your opinion.
Okay, thank you. I think it depends on our technology on shielding, but I think in the near future we may stay on Mars for several years, even more than 10 years.
Okay, thank you very much. And thank you very much, our speakers. We are almost on time. We have 2 minutes left for a coffee break. And thank you very much, the audience. It is a very nice conference, very nice place to meet and to see. And I'm happy all our panelists are optimistic about human presence in space. Thank you very much.
Thank you very much, Anatoly, and a great thanks to all the speakers. It's really encouraging to hear the opinion of the specialists that are quite optimistic in terms of how long humans will be able to stay in outer space. That's all very encouraging. Thank you very much. This is the first session that was actually closing at 2 minutes before the end, so we have 2 minutes more of coffee break, and that's where I would like to invite you now. But I would like to remind you that at 11 o'clock, our conference will continue with the 6 technical parallel sessions, and here in the room we'll have another very interesting global networking forum. So please make sure that you are in the rooms of your choice some minutes before 11. Thank you very much.